Okay, says we're live now, so we'll wait 10 seconds for the stream to catch up. And then goes the jingle. Okay, here we go. So hello, everyone. This is ZuriHack 2021 again, and this time we're at the GHC Ask Me Anything panel discussion. We have as our panelists here Simon Peyton-Jones and Ben Gamari, and they are here to answer all your questions about GHC. And the way this works is that we have already collected a couple of questions before, and you can also, when you're attending ZuriHack, ask some questions live, either via the ZuriHack Discord in the corresponding GHC panel discussion channel, or if you don't use Discord, you can also ask it via the Libera Chat IRC channel, and I will just try to relay those questions to our panelists. So first, a little background. We have Simon Peyton-Jones, of course, like ultra long time contributor to GHC, master compiler writer, and boss of all type systems. And we also have Ben Gamari, current release manager, and fixes pretty much everything in GHC that doesn't work. So yeah, I guess we can perhaps start immediately with some questions.
Yeah, do you want to show a link to the Discord in the chat?
Yes,
so
I
can have that up too.
Yes, this you don't need to do. Actually, I will read the questions for you because we will also have a delay. But I can also post the questions.
Wait, no, Ben has. It's fine. Yeah.
Okay, then it's okay. I will also try to post whenever I get a question from the Discord. I will also post it in here in StreamYard in the side discussion. So just in case you want to go on some longer answer, I will put it in there so that you can see it. So the first question that we got so far is, what do you as GHC developers think about a new Haskell report? Has GHC given up on that, or is it just replaced with GHC proposals? And what do you think would be needed for a new report? Do you think it will happen?
Want to take this one, Simon, first?
Yeah, you could start.
No, go for it. All yours.
Okay. It turns out that writing a language report, a complete specification of a programming language, is a lot of work. I was the on the committee that wrote the original Haskell report, and then particularly I chaired the process of getting to Haskell 98, which in the end came out as a book published by Cambridge University Press. And I can tell you, it was a lot of work. So the difficulty with getting a new, as it were, iteration of Haskell in that style is that there isn't enough incentive for anybody to step up and do the job. We've had sort of repeated attempts to do that, but in the end, we just haven't maintained the momentum. And I think it's because everybody wants it to happen, but really everybody wants somebody else to do the work. And also, it's not just that it's work like digging a hole. It's work that requires a lot of consultation and discussion, and which there's never going to be complete agreement. So then the sort of Haskell Prime process was an attempt to kind of somewhat reduce the barrier to entry, reduce it into more little increments. But I think in the end, the Haskell proposal process has somewhat, has ended up being much more successful in process terms. So we try to write individual increments to the language to get fairly thoroughly discussed by the community. It's not the same as a single integrated language report, but it's a lot better than nothing, because previously it was more or less anybody who had their fingers on the GHC commit bits could commit something to GHC, at least if they could get it past me and Simon Marlowe and such like. And that was much too small a circle of people. I feel as if there's many more people have a voice, both in making suggested changes and in critiquing design changes than happened before. So I feel as if the door is still open for somebody to write a new iteration of the Haskell report, but I feel as if the reason that it's hard for everybody to sum up the motivation to do so is that the language that people use tends to be Haskell where she is now, largely as defined by GHC, and a Haskell report would tend to be, a new language definition, would tend to be quite a way behind that curve. So then you think, well, do I want to spend all this time defining a language that isn't the one that people are actually using? So it's a social problem, not a technical one, I would say. And I would welcome a new iteration of the Haskell report, but I'm not very confident that it will happen. What's your view, Ben?
Yeah, no, I think that's right. I mean, it's pretty clear that the GHC proposals process does not replace a report. It's much, the degree of sort of specification is certainly a bit lower, less precise, less capable, less able for another implementation to come around and implement it potentially. And it's generally more speculative. We don't know that these are the features that we want to end up in the language ultimately, even if they do make it through the proposals process. But yeah, it's clearly a difficult thing to get a group of people through the prime process to a point where they can actually start to put together what will become a new iteration of the report. And the fact that it's sort of been tried a few times now and kind of fizzled out on every occasion.
Yeah, not with acrimony. There was no great difficulty.
No,
it was just energy. And I think I do think there's if you think, what are the impediments to what are the obstacles to getting Haskell used in practice? I don't think the lack of a book that defines some increment on Haskell compared to the existing materials is the primary obstacle. There are lots of other obstacles, to do with education or tutorials or library support or tool support. But or even sometimes language features, or perhaps the compiler itself, or Cabal or Stack or something. But I don't think the primary obstacle is the lack of a language definition. And so at some point at which it becomes a primary obstacle, well, then I think that would energize people to focus attention on it.
But I think that actually also brings up a good point in that the sort of impetus to try to put together a proposal. I think a lot of people want a new language iteration simply so they can say default language equals Haskell 2021 in their Cabal file and get sort of immediately the extensions out of the box that they have come to expect out of Haskell and rely on a day-to-day basis. But now we have GHC 2021, which is not a language specification, but it does give you that name of the set of functionality that people sort of rely on this year. And I think that may also sort of take further wind out of the sails of any potential standardization process.
I suppose it's not just the name, Ben. It's also that the GHC 2021 is a collection of language extensions which work well together, and there is some quality control mechanism there. So there is a process that the Haskell, the GHC steering committee went through to decide which should be in and which should not be in that set. So that, if you like, is, as it were, the proposals process defines the features, and then this sort of process that comes up behind identifies collections of features that collectively might constitute Haskell GHC 2021 or GHC 2023, and that's serving the kind of same role, not and it's a lighter weight process. That's the advantage.
Yeah,
and therefore it's
but
one
it's
that
still
might
not a
happen.
report, obviously.
Yeah, that's right. So none of it's a report, but so it's. I mean, this is really an invitation to anybody listening. If this is your primary problem, then maybe you could be a primary contributor to a solution.
Yeah, I'm going to ask the next question because by now a big list has actually built up.
Good.
So first, there was a bit of feedback here, which I will also post here. Somebody pointed out that the well-typed GHC activity reports are great. The question is, would it be possible to see something like this that covers all of the GHC contributions, or is this perhaps already the case of those reports?
So for a long time, we actually did something like that, or well, I say for a long time, for
10 years plus.
Yeah, I suppose that's true. It was a long time. And there was a weekly or bi-weekly or monthly, it was sort of the period varied over the course of the project, but report, blog post, sort of in the same style as the well-typed status report, which we tried to put together that summarized not just, sort of the core contributor contributions, but also, the whole ecosystem, GHC in particular. It took a lot of work to put that together. I mean, it sounds hard to believe, but it's actually going through on a weekly basis and trying to distill the bits that sort of are worth mentioning, and then summarizing them and doing that on a weekly basis. It was a fair amount of work. That being said, it is really the fact that the well-typed status reports have had so much traction and clearly have been a worthwhile contribution does make it easier to see the payoff of that work. And so it is something that, yeah, I mean, thank you for bringing that up. It's really good to hear. And
again, another thing to point to is that for quite a while the Haskell Communities and Activities report was coming out twice a year, over a period of, I think, 12 years, we wrote, every 6 months we wrote a GHC status report. I put a link in the chat here. Maybe you can reflect that on the Discord server somewhere.
Yeah.
So at the bottom where it says biannual status reports. So, and we stopped doing that, I think, when we ceased having the provocation of the Haskell Communities and Activities report, which then itself stopped with a lack of volunteer. But I think that's a useful function of the same kind. Every 2 weeks is quite a lot of work. Every 6 months seems like more feasible. But one thing that would be really helpful, and again, this is something where, that lots of people contribute to GHC, it's a big project, would be to have an editor for the, the GHC status report. Maybe you'd have somebody who would act as the editor and say, guys, deadline coming up, please submit to me your paragraph or two about what you've been doing with links, and I'll collate it into a coherent overall report. That would be a really helpful thing to do. And I don't think you need to be an active, code contributor to do that. You could be our, the communications contributor. That would be really helpful. GHC is a big open source project. It needs everybody. There's meant to be an open door.
Yep.
Yeah, that sounds like a great place for community members to start at, right? Because you also get a lot of experience of what people are working on. Another question that we have here is kind of a bit of an opinion question, I guess, but also technical. What do you together consider the cleanest parts of the GHC code base, or the ones that you're the most proud of, and which ones are the worst ones or the most difficult to work with?
Simon, do you want to take that one first?
So the bit that I'm the biggest bit that I'm proud of, which I think most of you will already know because I give talks about this, is GHC's core language. This is a little intermediate language that sits in the center of the compiler. Haskell, this gigantic language is all compiled into this tiny core language, and it's a statically typed core language in this really rather rich type system involving casts and coercions and evidence as well. And that language has been very stable. GHC is 30 years old, and the core language, the only addition we've made to the core language in 30 years is adding casts and coercions, which was a big one. But nevertheless, now surrounding that then are lots of analyses and optimization passes that work over it. Some of them are better engineered than others, but I think because they all share this common data structure, the core language, I think I'm pretty pleased with that. I'm also happy about the type checker. It was I guess it was about 10 years ago, we made a complete reorganization about the type checker that I described at ZuriHack 2 years ago, when it moved towards instead of sort of something rather ad hoc, it moved towards a systematic approach to doing type checking by generating constraints from the syntax tree. So a very large syntax tree, many constructors have a constraint generator, and then a constraint solver that works over the very small language of type constraints. And that architectural change was huge, and it's made a big difference through the life of the type checker. And for example, we've recently added this quick look idea to checking impredicative types, and I think that would have been hard without that architecture. So those are two pieces that I'm quite proud of. Well, one of the pieces that I'm less proud of is I was saying to somebody just yesterday, I think if I had £1 for every hour I'd spent thinking about eta expansion and eta contraction, I would be a rich man. And I would never have said this 30 years ago, right? Eta is when you change f into lambda x fx, right? So it's kind of it seems like a very innocuous transformation, doesn't it? Or maybe when you change lambda x fx into f. So you add or remove lambdas, but it has a profound effect on the arity of functions, and the arity of functions in GHC says how many arguments they take is very important for the optimization phases to work well. But it's not as principled and well tied down as it should be. With Paul Downen and Richard Eisenberg and colleagues, who wrote this paper, Kinds of Calling Conventions, which is a one take on trying to fix that, but it's quite a complicated take, and we have not fully not implemented at all, really. Though a student Shant is working on that right now. But I would say that's a sort of wobbly point inside the compiler. What about you, Ben?
Yeah, it's a good question. I mean, GHC is an old project, so there's a lot of very unclean pieces, and I think thankfully we have contributors now who are doing active work to clean up a lot of this. I mean, Matt Pickering has recently been working on cleaning up the front end and sort of the driver aspects.
Yeah, the driver. The driver is a good example, right? You think driver. What is the big deal, right? It invokes the renamer, it invokes the type checker. It invokes the CPU processor, it involves how hard can it be? But the driver has grown into a monster of spaghetti, which Matt is busily cleaning the Augean stables of, and that's what happens with very old projects.
Yeah, and I think Sylvain Henry has also done a great job in just the overall project structure. For a long time, Haskell was sort of this very flat module hierarchy. There's not a whole lot of sense from the module names what the relationship between these pieces are, and thankfully Sylvain has done a great job in sort of trying to make sense of this and put it into a more modern structure where it's among sort of the same structure that you would expect to see in a modern Haskell project, and that's something that is a lot of work, and it takes a lot of sort of understanding of the compiler to do. So as far as the bright spots, it's a tricky one. I think perhaps only because it's something that I've worked on more recently. I was really pleased with ultimately how the new garbage collector fit into the overall shape of the runtime system. It is a rather different approach to garbage collection than the current collector that the existing copying collector, and yet somehow it just fit very nicely into the storage manager, into into the mutator and the sort of barriers that we had to include in the mutator. It all just hung together very nicely, which I was frankly, this was one of my greatest concerns when I started that project, is that it seemed like it was sort of just be a bolt-on addition that we'd end up having to maintain, and it wouldn't really fit nicely into the existing project structure. But it in fact it ended up being quite nice. I think it's actually a sort of testament to the design of our backend and the runtime system that supports it, that this all was relatively easy to do after a bit of refactoring.
Another big thing that's being refactored at the moment is error message generation. So error messages up to now have just been strings essentially. We're slightly better than that. Now they're all being turned into data types. But that entails a sort of heart-lung transplant on the entire error message structure. This has been done by colleague Richard Eisenberg's, and I think with together, I think it's Pedro and
Alfredo is
Alfredo. That's right, yeah. Alfredo. That's really a big piece of work. I mean, it is interesting that though GHC is a very old piece of software, it's 30 years old, yet we do these very large-scale refactorings throughout. And I, in turn, put that down to the fact that it's written in Haskell, that we can do that and still have it work.
Yeah.
Another related question that is coming up here is, what are the current midterm projects or plans for making GHC more reusable as a library? So, for example, currently we can reuse the parser for our tooling, but what we actually need is the renamed AST. Will we be able to do that without depending on everything else up to code generation?
There's already actually been a lot of work that's gone on in this direction. So, we've now within the GHC tree, now there's the Haskell language AST is actually living in a separate part of the module namespace, with the eventual goal of hopefully, and this is again supported by a rather long-lived effort in the trees that grow area to sort of rework the AST itself to make it more modular. So now it actually exists as a separate sort of part of the source tree, and the goal there is hopefully we can at some point move it out of GHC entirely into its own distinct library, and we'll have to that will take time without a doubt, and then the renaming and type checking and the things that happen to that representation. Indeed, there's a lot of work that needs to happen to make those bits sort of reusable and nice to work with from the GHC API. That's something that really, in large part, we just need users to come to us and say, this is what I want to do, and this is where the current instantiation of the current API that we express, that we offer rather, falls short. We currently sort of define the GHC API to be the GHC module. It's a single module. It's a very large module, but you can look at the documentation on Hackage. But it's a single module, and obviously exposing everything you'd want to do with the compiler from a single module is this is clearly not realistic. But the reason it's just that single impoverished API, and indeed you can't do a whole lot with it, is that people haven't really come to us and said, well, we also need this interface. And people have in the past suggested that, well, maybe we should just have the entire source tree be a stable interface. But that's obviously not sustainable, right? We need to retain the ability to be able to evolve the compiler and be explicit about what the stable bits are and which the internal implementation is. And so that's really what we need, is for people to say, I want to do this, and I think this interface, these 5 functions would be very helpful in accomplishing that goal. And then we can work to making those stable, or potentially refining the interface to become a stable one. Mm-hmm. It's a hard question, though. I mean, that's something that really we do need feedback.
Yeah, as you say, it's a partnership question, right? Because it's not the sort of thing that we can answer ourselves as sort of the GHC authors, and has lots of different components. So that the one thing that Ben mentioned was making the AST itself into a reusable component, right? In a separate library, and that all by itself is quite a big engineering effort. But it's fairly well advanced now. This is the sort of trees that grow idea. Trees that grow is just the name of the sort of idiom. You can find a paper, just search for a paper with that title. It's the idiom that we use to structure the AST so that we can have a single AST that could be used by anybody who's processing Haskell at all. And then GHC describes sort of GHC specific decorations that fit on top of it. And that all fits into a statically typed language. But then there was lots of other things, like in the questioner specifically says, what we need is the renamed AST without depending on everything else. So there's a question about, could we, as it were, have part of the GHC API without in some way depending at all on the code generator, like a subset of GHC? And we've made no serious attempt to do that, and doubtless it would be possible because, of course, the renamer doesn't depend on the code generator, but it would require work, right? It would require somebody to go through and say, what are the dependencies and why does it depend in that way? And what would it take to refactor a bit to cause that to happen? And again, that's something that is never going to happen by itself. It's going to need someone to say, this is important to me. I'll help. So I think what we want to say from our end is those kind of things, if somebody wants to do that, then we would be, supportive and try to help you move along, and certainly not stand in the way of that kind of refactoring. And again, because it's written in Haskell, we can do that kind of refactor and keep it working. Another component is, what should the APIs be? Never mind what you're depending on. What should the API be, right? And also, how stable do we want it to be? So if you have a very large API, which quite a lot of plugins use quite lots of bits of GHC, it's very hard to keep it all stable. Very small API, easy to keep stable. And we need, I feel as if the more that GHC becomes used as a library, the more that we'd want really kind of like a committee to watch over its API and to say, this is the bit that's important to us. Because otherwise it evolves a bit at random rather than by design.
The next question will be about guarantees in terms of performance. So one question was, has any progress been made on optimizer guarantees such that an assertion that a wrapper would never appear in a final compiled program? Should something like this be done, for example, as a compiler plugin, or what would be your recommended method of obtaining such assertions?
I think that there is indeed already work along these lines. That would be Joachim Breitner's inspection testing. And I think this is a really underutilized tool. We've actually been, so Andrew Ledachenko, in working on byte string and text, sort of in the context of recent Haskell Foundation efforts, has been using them to using inspection testing to verify fusion and sort of related properties of text and byte string, and it's revealed some rather shocking bugs. I mean, it really has given us a much better sense of where things can go wrong with the mechanisms, fusion especially, that we have currently. So I think that really is most of the solution. Could we move it into GHC? Perhaps, but there's also the question of whether that is really something that would be what value that offers. I think it would be great though if it became sort of a like criterion or quick check, sort of part of the typical tool belt of tools that Haskellers rely on to gain certainty of their code's correctness would be a great direction.
So I think the great thing about inspection testing, it sort of tells you when something isn't right, but it doesn't necessarily tell you how to fix it. So that's a difficulty with this thing about guarantees, is that if you want to say, I think maybe the question is asking something like, I'd like to be sure that fusion has happened. So I don't want to see any occurrences of this data constructor in my final program. But if GHC sees an occurrence of that data constructor, it's not necessarily obvious what to do about that. So I think there's a research question here. I don't think it's just a question of cranking the handle. I think that the very nature of the guarantees and what guarantees do you want, how might you check them, and particularly how might you establish them, is a really good question. I think would be worth work.
Yeah, that's true. And I mean, we typically, Haskellers especially have the tendency to, we build these wonderfully elaborate systems for ensuring that things fuse away at compile time. But then that also, there's sort of a double-edged sword there, in that then we end up with rather long compilation times because we do a whole lot of inlining, a whole lot of then simplification on that inlined code, and that gets repeated again and again and again due to the way that inlining occurs in GHC. So this is something, how do we have our cake and eat it too? It's a hard, indeed, there's research to be done there. It's not clear, but we have seen, there's a ticket open right now against GHC 9.0.1 in ASON regressing in compilation time pretty profoundly. And it's simply because of how inlining, now we do a bit more inlining, which produces significantly larger programs. There's good reasons for that inlining. And indeed, it's quite beneficial to runtime performance, but it also costs quite a bit in compilation time. So there's work to be done.
The next question is probably quite a broad topic, so maybe we should just have some short summarizing answers about this. And that question is, how far are we from a fully dependently typed GHC? So now there have been many talks in the past years about various progresses in dependent typing. So maybe a short summary of how far this work is overall, or like which parts are still missing until you would say, okay, GHC now has a fully dependently typed language that you can use. And I guess another way this question could also be interpreted is I'm not sure if this was the intent of the author, but another question would be, would you maybe be interested in using dependent types in the compiler code itself in the future?
Simon, maybe perhaps you start with that one.
Yeah, so I think a good thread to read here is the GHC proposal about dependent types. It's I think it's 378. I'm just trying to find a link to it. Maybe you can do that while we're speaking. So there's a lot of discussion about but the proposal itself now includes, the proposal itself was meant to be a not a specific design for dependently typed Haskell, but rather a description of the direction of travel, if you like. So the first thing to say about to the answer to the question, the person asking the question is, there isn't, the spectrum of dependently typed languages is itself very large, right? So it's not a one thing; it's kind of like a space. And GHC has been moving, gradually towards that space anyway over some time. So this isn't, I don't feel as if this is like a, a sudden Rubicon we're going to cross. It's more like, we're moving in that direction. I think it's one of the things this proposal does helpfully, though, is to sketch in quite a bit more detail what shape of, which flavor of dependently typed language Haskell might evolve into. So rather than just generally talk in vague terms about dependent types, it's much easier when you start to tie it down to specifics. So if you're interested in what a dependently typed Haskell might look like, look at this proposal, but because it's long, precisely because it sketches an approximate language design, and so brings focus to the conversation. I think we'll we'll move slowly in that direction, I think one of the Haskell has always been, and GHC specifically has always been, both a a production tool that people can rely on, at least that is our aspiration, and also a laboratory in which we can explore the bleeding edge of what it means to be a programming language. Well, certainly what it means to be a statically typed functional programming language. So, and these two are clearly in some kind of tension, right? The tension between a reliable production tool and a sort of bleeding edge laboratory pull against each other. On the other hand, I would say that quite often the people who ask most strongly for some of these what you might think of as rather exotic type system features are the people who are working in industry, right? They're not just pointy-headed academics or PhD students. I think it's very intriguing. And I think it's because people in industry are writing Haskell programs that they want to work in 10 years' time. They want to be sure they're right. They're not going to throw them away tomorrow. So they want the security that static type systems gives you. So, so I think though there is a tension, yet it's a kind of creative tension, and one that I think Haskell has successfully navigated for a long time, and I hope will successfully navigate for some time to come. So I guess my answer is isn't going to be a sort of Rubicon day. I think that is the direction in which we're likely to move at a pace that's governed by not breaking too many people's programs and what commands broad consent. We've got a sort of established direction of progress, though.
To sort of address the second half of the question, which I think was whether GHC itself will start to move in the direction of more static guarantees in its types. I suspect the answer to that is it may be, but very, very slowly. If you look at, for anyone who has looked at GHC today, you know that it's not exactly it's a different flavor of Haskell than what you often see in commercial projects, and there are reasons for that. And it's already, writing a Haskell compiler is already a very, very difficult domain. And indeed, there are real advantages to having static assurance that the compiler is doing something sensible. But we sort of have to, it's very, very difficult to prove this in a type system.
So some of the invariants you might want to satisfy, like no variable that is not in scope can be mentioned, right? Which is something you like to write an optimizer that statically guarantees it can never produce an ill-scoped program. Well, that is a research question that people have worked on, but it's a pretty challenging one to maintain and still get your optimizer to work well, for example. So maybe the kind of invariants that compilers want to maintain are harder to express in type systems. Perhaps that's but we certainly use type families quite a lot these days. Certainly in the trees that grow stuff, there are lots of them.
Yeah. So we will see. Really see what research brings.
Next question is another very technical one, which is we unfortunately don't have Simon Marlowe on the call currently, but do you know if there are any considerations or interest to rewrite parts of the runtime system in Rust, probably for added runtime safety?
It's an interesting question. I've actually I've thought about this a fair amount, not just in the case of Rust, but also with C++ and various using various static analysis tools on the runtime system, because it's the GHC runtime system is a remarkable piece of engineering. I mean, Simon really deserves a great deal of credit for this. It's a very complex, parallel, concurrent program that sort of straddles the line between the mutator and the operating system, and it does so remarkably well. And yet there are bugs, and we've had our fair share of runtime system bugs, especially things like linking are very, very challenging. So yeah, there clearly is room for better static verification. I suspect the direction, whether or not Rust is the right decision or the right tool to provide that verification, I am not sure. It would be an interesting project. I wouldn't, sort of as a research topic, I guess, in a sense. To see how the strengths of Rust sort of fit to address the weaknesses of the runtime and its potential bugs that it might exhibit. I suspect it's not the quickest way to get to that end, though, to get stronger verification. Rewriting is it's not something you undertake lightly, especially in the case of a project like GHC's runtime. It would be a very, very large undertaking. And I suspect you could probably get most of the sort of fruits of that by rather just employing existing C static analysis tools. I've looked into this on a few occasions, and there are some pretty compelling answers there, pretty compelling options that we might consider using. The Mono people have an analyzer that they use for their own runtime system. They have, at least, called Ward, which I think is a really nice point in the design space, in that it's not invasive, but it does allow you to express some very nice invariants that it can verify. So
I think the runtime system lacks love, isn't it? That is, there are very few people who know anything about how the runtime system works. I mean, including me, I really don't. You know,
no, that's right.
Simon Marlowe is the king, but he's. But I think we could. But I think we could really do with people who would love the runtime system and get to know it well and understand it. Because at the moment, it's one of the bits of GHC that I feel less, not confident about, but I feel less secure about, because I feel we do not have strength in depth for for fixing or improving it, if that becomes an important thing to do.
Okay.
Yeah, that's right. So if you're interested, if this is something that you want to look at, and maybe Rust is your language of choice, then by all means get in touch, and we can maybe can talk about potential options here, ways that we could explore that opportunity. But yeah, there's no effort afoot, if that's the question.
We have two GC questions also. The first is about old GC stuff, which is, what about the old compacting collector, so plus RTS minus C? Is that still safe to use in production? Is it worth keeping?
It is. I mean, we still maintain it. We've fixed bugs in it recently, in fact. Is it worth keeping? Yeah, boy. We ultimately need to keep it, I think, as long as we have the moving collector or the copying collector. We pretty much have no choice, in that it is the only way that we can ensure that copying collection does not sort of blow through our memory allowance. In general, whenever you do a copying collection, you need to double the size of your heap. Currently, if it looks to the runtime as though, if we do so, it will blow through its heap allowance, its size allowance, then we will fall back to a collection, and that's how we ensure that we don't blow through the.
So we are silently using compactor collection anyway, are we?
Yes.
Right.
So you do use it, even if you don't pass RTS-C potentially. So yeah, I think it's worth keeping. I think we have to keep it.
Just small follow-up question from me, from my personal usage of the compacting collector. My understanding is that this is really what you must use if you give the flag that just bounds the total amount of heap memory that Haskell uses. So let's say you deploy something to containers or what, and your container must have maximally, 10 gigs of memory, right? That if you want to make sure that you use, let's say, I think it's the -M option or something that gives the maximum memory, then in order to make sure that you can use more than half, right, so that you can do a full copy, you must use the compacting GC to get those guarantees that you will never exceed that. Is that correct?
My recollection is that we should already be attempting to fall back when it shouldn't be necessary. I may be mistaken.
I don't mean that you need to enable it. I'm just saying, this code is in use.
Yes, that's right.
It will not be removed.
Yeah, that's correct.
Yeah.
Yeah.
Okay, then another question about GC is there really no timeliness guarantee on garbage collection of resources such as pools? Would rewriting, for example, data.pool with refinement types totally address this? My understanding here is that this question is asking, are there ways how we can maybe give more finer control about GC to give timeliness guarantees?
So pools, I think there may be a few things going on here. So pools, I think you're referring to data.pool from resource pool, the package.
I suspect that this is what the question is referring to. Yeah.
So, and in that case, that largely is going to, the thing being pooled is often like a foreign resource, not memory per se, but like a database connection or something like this. And so in that sense, we don't we shouldn't really be incurring long GC pauses due to pools anyways, I would hope. There is, though, the question of whether, if you have a highly allocating workload and it may, you have a server, for instance, it needs to allocate, tens of gigabytes of stuff in the course of serving a connection or a request. You might think that, you might want to have GHC rather use some arena allocator and just accept the fact that the heap will grow, in a bounded manner until the request is finished, and then just, sort of dispatch of the entire arena at the end of the request. And that's something that I've thought a bit about, actually. It seems like a opportunity that we do potentially have the means of addressing. We have compact regions, which kind of allow you to do something similar to this. If we could allocate directly into a compact region, for instance, and then and throw away the compact region, essentially use the region as a nursery, and then throw that away at the end of the lexical scope. So you're doing evaluation within a compact region. That would be an interesting approach, which I think has some legs to it. It's a bit tricky. There are some details there that I've sort of that are a bit tricky to resolve concerning CAFs and details of the evaluation model. But I think that is an interesting point of inquiry, and I'm hoping, I mention this periodically, hoping somebody sort of picks this idea up and tries to run with it. But yeah, so far.
I think is the question to do with timeliness guarantee on garbage collection of resources? I think that means any kind of guarantees that a resource that you're no longer using will be explicitly recycled or by the garbage collector.
Oh, timely. Yeah, that's true.
Timeliness guarantees. I think maybe
I had misunderstood the question. Yeah. So that you can be guaranteed that a resource only lives, a bounded time after it really becomes unreachable, I suppose.
Yes. Well, except I'm thinking aloud here, but even becoming unreachable, that's an approximation to will be never be used, right? But something might be reachable in the data structure sense, while actually never being touched again. So the trouble is that it's really hard to know when something will never be touched again. And I think our best story for that is actually this linear Haskell experiment at the moment, which is another example, incidentally, of GHC being used as a vehicle for a laboratory for an idea. So there, that you can read about in the papers about linear Haskell, but this is actually implemented in GHC and does provide a way to give, you have to play a more explicit role as the programmer. But I think when you care about timely garbage collection of large resources of external, you may want to play a role so that you can be sure, so that you get some guarantees. And linear Haskell is not the only way to do that. I mean, Rust has another kind of story on all this kind of thing as well. So that's why you need laboratories to try out ideas to see which work best.
Another question is about performance regressions. So one asker asks, I've seen some significant performance regressions in 901 in the Streamly package, which is a streaming library. Is it possible to stabilize the inliner in some way or have more regression tests to avoid performance regressions?
There are two parts to that question. Is it possible to stabilize the inliner? Well, that's something, historically, we've not really considered the specific behavior of the inliner or the simplifier to be part of GHC's sort of stable interface to the user. We do document some of the behavior in the user's guide, and that should be stable. But particularly when we choose to inline and what happens as a result of simplification after that, less so. So stable, it's very difficult. I think we'd be a bit reluctant to really codify, especially inlining heuristics. That would become very.
Yeah, it's true, but at the same time, this particular library has been a very interesting sort of journey over the last 6 weeks or so, because its author and maintainer, is it Harendra? Is that how I know him as his handle? Has been incredibly helpful in providing well-characterized reproduction cases. So he says, look, check out this repository, check out this thing, compile it this way, compile it that way, you'll see a difference, and it's a substantial difference. And that makes it possible to get at. So then So then I, in fact, have spent quite a bit of time in the last 6 weeks looking at this very library, aided by these fantastic repro examples, and found several places in which we really can increase stability. So in effect, the previous version of the library was accidentally exploiting a kind of fluke that happened to work, perhaps because the authors had moved things around into a configuration that just about persuaded the previous version of GHC to work. And then, but it turns so one of them, for example, was rewrite rules were being oversensitive to eta abstraction and eta reduction, so a rewrite rule was not firing that was firing before because something was eta expanded. Now, an eta expansion is meant to be a pretty benign benign change. So since then, it hasn't quite landed. I've got a patch that makes the rewrite rule system insensitive, or much more insensitive to eta expansion. So that's I think a definite move in the direction of stabilizing, right? So it makes the thing less fragile. Another example was in a particular function, the authors in this library had written some inline pragmas. They were to try and say to the inliner, look, it's important to inline this function and not that one. And it was a very specific situation. It was a local binding of a mutually recursive group, and they were trying to say inline these ones of the mutual recursion, but not those ones. But it turned out that due to a long-standing bug, these particular inline pragmas in this particular setup were being ignored, but nobody knew. Right, so but nevertheless, the thing ran fast because it just happened that everything worked out. But in a later version of the compiler, it didn't work out anymore. But because we had the reproduction case, we found this, and so I've now fixed it. So it doesn't ignore those things. It behaves. So now again, it will behave in a stable way. So I think that the whole thing about pragmas in GHC is meant to give you some control over inlining and other optimization behavior. And I'm really keen that as a principle, it should not be the case that small changes in the compiler or a program make big changes in performance. So if that's happening to your library, it's really helpful if you can boil it down to a reproduction case with very, very direct reproduction instructions. And that gives us some chance of getting at it. I think we can make material progress. It isn't just, do this other random thing and it'll work for a while. We can actually make progress. But it's hard to know these things can lie hidden for a long time because nobody knows about them.
To sort of refine my previous statement, I guess what I mean to say is we'd be reluctant to make guarantees about, like sort of freeze the stabilizer, the simplifier and its behavior, its inline heuristics, etc. But we do hope we can make it more reliable, so more stable and
predictable. Yeah,
and predictable. The other thing is, I think, which kind of comes back to a previous point. The second half of this question is more tests and being able to, on our side, sort of verify that we aren't breaking downstream programs. And that is indeed something that we are very keen to do. So this is something that we've actually focused on relatively recently. We now are in the process of taking the head.hackage patch set and running this as part of our sort of typical CI routine. And currently we're just testing that things compile under that, and that's already found a good number of regressions before they've made into a release. But what ideally we'd like to do is also run test suites and potentially benchmark suites, but test suites are very easy. And if users who have sort of performance expectations of their library write inspection testing tests to ensure that, for instance, fusion occurs, or that the performance characteristics of their library are preserved, then that will allow us to get better assurance of the correctness of GHC's simplifier and make sure that we don't break things, or at least we know when we do so. And so that would be very helpful. That's a way that package authors can really help.
Yeah, we're trying to sort of open up that partnership. I don't know. I think we could probably do a better job about communicating on that front, Ben. Don't you think that it would be?
No, that's true.
Because it's the kind of thing which it's awfully easy for GHC authors to say, well, it's a library problem, and the library authors to say it's a GHC problem, and both things are quite complicated artifacts. If I look at Streamly, I haven't got a clue what it does or how, right? So I have no chance in really figuring out what's going on. So it really is something you have to get the two people talking to each other.
Yeah.
The next question is about complexities of algorithms in the GHC itself. It goes as there are various algorithms involved in parsing, type checking, code generation, and so on. And the big desire of users is GHC to run faster, and various people seem to be working on that currently. But it would be cool to empower more contributors to that. So for these questions, I've heard that some functionality inherently has a high computational complexity. For example, I've heard that generics, type checking and working with generics has a high complexity. And I remember it being exponential in the term size. Could you give us together an overview over which key algorithms in the compilation code generation process have which complexities, and whether those are already the theoretically optimal ones, or if that would be a place to improve something, let's say from, I don't know, cubic to quadratic or whatever. How do you judge the current constant factors in GHC implementations? So, for example, you could say, I don't know, this concept is linear, but it has like a terrible constant factor, and this is something that people should work on.
Yeah. I mean, there are a lot of, in general, we strive for GHC, the compiler as a whole, to be sort of linear in the size of the program. But there are some cases where our internal representation makes that very, very challenging. So, the example of generics is given here. Type families can be another one. This is something that, is a rather long-standing ticket, 8095, that Adam Gundry is actually currently working on, where type family reduction can blow up in a quadratic way. And so the input program appears to be linear, or appears to be of a reasonable size, but then it blows up in a sort of quadratic way after type checking. This is something that obviously we want to fix, but it's rather tricky to do, and there's sort of trade-offs involved. So in the case of the type family case, we've spent a long time playing around with this idea of zapping of coercions, or the thing that's blowing up in the type family case in 1895 is coercions, which are sort of an artifact of type family reduction, which can greatly increase the size of your program if you have many reductions. It's a bit, however. So we played around with the idea of sort of just dropping them entirely, replacing them with placeholders instead of the coercion is essentially a proof. Instead of representing the full structure of the proof, which we don't really care about, it's not runtime relevant, we're just going to replace it with sort of trust me. And that ended up being a rather tricky thing to do, or to know when that's actually a favorable, a beneficial change. The same sort of, in the case of generics, it's actually even harder. And Simon has a paper about this topic from around 10 years ago or so, scrap your type applications. The generics case is really one of the elaboration that GHC does, adding type applications which grow sort of linearly in the depth of an expression, which in the case of in the case of generics rather, and that can end up that ends up being quadratic in general if you have a very complex type in a generic representation. So yeah, we have, that paper describes one way forward, but it's not actually, we don't know that it would be a worthwhile change, and it's a rather non-trivial change to make, but it clearly is affecting users, and generics is one of the.
It's worth saying that it's typically not one of these, I'm using a quadratic sort and I could use an n-log-n sort instead and achieve exactly the same outcome, but with a more efficient algorithm. I'm not very optimistic for those kind of changes in GHC. There's some places, like with some people who use GHC are using GHC with like 10,000 modules in GHCI, and then they make a change to one, and they don't want to wait very long before reloading it. But it turned out that we were somehow visiting all 10,000 and taking too long with each, so it was taking multiple seconds to just get a tiny change absorbed, and so that is something which you wouldn't notice if you had half a dozen modules. You start to really notice when you have 10,000. So there are some of those, but I think the in terms of, we paid a lot of attention to making GHC run faster. I think the questioner is right to say a big desire of users is for GHC to run faster. That is a big desire, but I'm pretty sure there's no really low-hanging fruit. And we have done quite a lot of profiling, and we do, CI now reports this and, you know, bites you if there's if you make anything go slower. It's very annoying. I don't think there's anything very easy to do that will make GHC go a lot faster. And I think we do have some systemic costs, which Ben alluded to, which is not algorithmic, rather sort of data structure. Because we got this statically typed intermediate language, the types and the casts that the coercions that give you confidence that everything is right can grow very large, and sometimes in pathological cases can go very large indeed. Now, you know, that's part of the cost that we have, you know, the hair shirt that we wear of having a statically typed intermediate language. If we threw away the types and just said, hey, trust me, you know, I'll compile all the way to machine code and I hope it's right, then we could be a lot faster. But that is part of GHC's laboratory stuff, is saying we're going to stay true to the statically typed intermediate language. So again, so I think it's a research question, and the paper that Ben referred to is one example of such a piece of research question, whether we can do substantially better. I think we can do substantially better on the casts and coercion fronts. That's the work that Ben was referring to. But I suppose I'm saying it's important to us. We know it's important, and we spend a lot of time on performance. But I'm not optimistic about any big gains, aside from the work that Adam's doing on shorting out multiple type family reductions.
So unfortunately, this had to be the last question, because we have been asked to end 3 minutes early, essentially, so that people have time to switch streams to the next upcoming talks. But thank you both, Simon and Ben, very, very much for answering all those questions. We got through around 50% of the questions that were posted so far. So I think there are a lot more questions that could be asked. But yeah, I recommend for anybody who has a remaining question to maybe post them into the GHC panel discussion channel, or perhaps also into the GHC IRC. There are a lot of competent people around, and maybe Ben or Simon even want to grab some of them.
Or the GHC devs mailing list is also a good place.
Yes.
Before we finish, we should just say that it is, as we've been stressing constantly, GHC is an open source project. It relies on volunteers to contribute. It's not, I know it's not a terribly easy one to get into because it's a large piece of software, but there are a lot of friendly people around, and they're very, you know, and they're very willing to help. So do please feel valued and empowered to join in, because really, you know, we need you, right? It's GHC will only flourish if it has you know, a strong contributor base. So please do that. And contributions mean, it doesn't just mean you know, an amazing patch that fixes the type check. It could just be you know, I've improved this error message, or even I've characterized a bug. Somebody reported this rather vague bug, and I've characterized it much better and made a you know, reproducible test case. All that kind of stuff's fantastically helpful. Or documentation, or communication, or editing the activity report. There's lots of things you could do. So please do. Thank you.
Okay, awesome. Thank you very much. And see you in the next talk.
Great. Good. Thanks.
Cheers, everyone.